Hey guys, hold on, let me have a sip of
Yeah,
water and then I guess effectively we can get started. It's 6:05, right? Yep.
and the way the talks goes over here, like it's the starting of the journal club. So first the talks will happen, and then we'll have us like 15 or 30 minutes to discuss the questions. So you guys like keep all your questions like
Uh,
collected for the meanwhile. Like what do you say
yeah,
first?
sure. Okay.
Okay, so
Yeah,
who is starting?
yeah.
Like who is recording? Like are you
I
recording?
am. I have been recording for a while. Yeah,
Okay, okay.
yeah. Do you, so. Can I start now? Yeah, okay.
Yep, yep, yep.
Okay. So hey everyone. First of all, thank you for being here. What we're trying to do right now is basically kick off this journal club here, and the idea is to sort of pick a paper and discuss it or host talks on that and so on. Again, this can be the way we're approaching this can vary a lot. But right now, with this paper, I just want to go over a few sections of it, which are very, very sort of non-technical as well. Uh, so to get into the paper, this is about an idea called gauge symmetry in theoretical physics, and the central goal of the paper is to just define these terms uh, pretty well. So that's one of the central goals, and that's kind of what we're going to be reviewing today. The rest of the stuff, I'm going to sort of hint to it, but this is mostly just a lot of index manipulation. So if there's one thing that you guys will have an idea about in the upcoming sessions of this, is that there will be a lot of index manipulation. So you'll get really, really comfortable with that. It's not a particularly interesting skill, but then you would require this one way or the other when you're doing physics. uh, so today is just going to be a non-technical discussion of sections 1 to 4, just the starting of 4, and then the next one will be a more technical one, and the one after that will be a meta one. So that's kind of how the paper proceeds. So there's a meta sort of discussion about if this idea of gauge symmetry is useful or not, and then it proceeds in a non-technical level as to to define these terms, and then there's a lot of lot of index manipulation to sort of show these ideas in practice in physics, in the context of physics, and then there's more formalizing of these ideas, like again, like Neko would sort of disagree, but this author does introduce covariant derivatives, the idea of just the GL group and things like that are useful for sort of formalizing what a gauge symmetry is. And then there's a meta discussion as to uh, is gauge symmetry a real symmetry or not. And as you'll see, the community is kind of split up about this idea. So uh, this this sort of black and white perspective begins in the introduction itself, when the author basically starts off by saying it's an important idea in particle physics. Again, I'm not going to go over this, but maybe in the next talk or so, we can go over some basic ideas in scalar field theory, and we can sort of see these things in action in a more concrete sense. Uh, but yeah, the biggest giants, the guys who write textbooks, they're basically in confusion, or they're very much for their own points, and both these sides make good points. Is the problem that this author is trying to sort of lead us towards. So you've got people like Frank Wilczek on one side, who claim that this is a very, very important principle, and then you've got like people like Nima on the other side, who are basically yeah, so he basically calls bullshit on this. So um, this is the idea that we're left with. So is this idea just a mathematical fantasy, or does it actually have some sort of relevance towards physics? And the point of this paper, according to the author, is to sort of bring some resolve into this uh, uh, by means of a meta discussion of how we got here in a historical sense, which is done in the very last section, and what is the most common argument presented in textbooks and why it's incorrect. So yeah, um, and as usual, as any physics talk should begin with a very honest throat clearing. This is a word that has been abused. Coordinate transformation, or the word gauge, or the word invariance or covariance, and you know it has been used out of context, and that is why we're sort of going under. That's why we're having to go under sections 2 to 4, where the author basically walks us through definitions of these words, um, and then he goes for the more technical arguments. So yeah, and the author alludes to this by saying the reason he does this is because uh, this hasn't been done, or most people already assume what that means. So yeah, today we will review what these words mean in the context of a toy model about currency exchange, and this is mostly going to involve a lot of stick figures and very 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 little math sort of kickoff. So if you're here for the math, sorry to disappoint you, but we do have a lot in store for the next session. So the discussion begins with this question: what is a symmetry? And symmetry is something that you experience, but you hardly think in a meta sense as to what it is before you begin a technical study of it. So the best example given here is a ball. So if you have a completely orange ball and you rotate it, in all sides, you do have a ball that looks similar. So you say that the ball is symmetric under rotation. So symmetry always has to reference what transformation you're doing to that object. So you can then say that the orange ball is symmetric under rotations. So there are some more examples given. So one example that you can quickly conjure up is if you have a triangle with black balls. So if you then rotate this, or if you keep rotating this is just going to be a symmetry. But let's say you have a different one. If this is your triangle, you certainly have symmetries, but then you're not going to get your symmetry under like a 120-degree rotation of sorts or something like that. So yeah, you have a more constrained uh, set of symmetries for this one versus this one. So yeah, but the point here is that a symmetry, when you're talking about a particular object, has to always reference under what transformation is the object displaying the symmetry. So yeah, and there are a bunch of different sort of types of symmetries, and it will be useful to understand them as we go along, because the most central question of this paper that the paper is trying to sort of uh, put out there, although we do not understand the words, is this a real symmetry or not? So we're going to track progress, and we know what this means, and we're slowly going to get to these two, and then we'll slowly get to addressing this question itself. So the central question of this paper is this a real symmetry or not? Is this a physically relevant symmetry or not? So again, physically relevant is two different words as well, so I will address that as well. So yeah, so this is pretty much common sense. So what's the difference between a global transformation and a local transformation? So you got a system and you got a bunch of subsystems within it, and obviously the assumption is that we are talking about sufficiently isolated subsystems. That is, these subsystems are not very much interacting with one another, or we can sort of exclude them from thinking of them as being interacting with one another. So when I say global transformation, I mean it happens to the entire system, this transformation. So this is basically what's called a parity transformation. So um, imagine your axes going this way, and you're pretty much just flipping the coordinate axes about 1 point. So the easiest way to represent this is if you have a coordinate x, y, z, this guy is going to read minus x, y, z along one direction. So yeah, this is the transformation, and this is a global one according to this picture, because it's done the same thing to every subsystem of the ship. So you can consider this to be a subsystem, the anchor to be one, or whatever sort of classification that you want. But the condition to call something a subsystem is that it's sufficiently isolated from the other ones, the other parts of the system. So yeah. And there's the opposite of it, which is a local transformation, which basically means you're making a transformation to a particular subsystem. And so yeah, the change made here is that we did a parity transformation for the bucket, and it is no longer so useful. So yeah. And this is a point that the author notes. At this point, we can note while global symmetries are common, local symmetries are rarely observed in nature. Um, yes, this is kind of obvious if you've uh, done a bit of field theory, but I will sort of detail this in the next session, or like towards the end of this session, as to why this is the case. Okay, so this is the other sort of category of transformations. So active and passive ones, and I just love this image, and I think I've used this a lot. Um, Neko will probably dislike this, given that how much I overuse this, but I think the distinction is pretty useful. So it so let's go back to the ball example, and if this is our coordinate system, so basically having XYZ axis is over here, and this is my orange ball, and it's at some XYZ. So a passive transformation is a transformation that you would apply to the ball itself. So you would, let's say you've moved it by some dx. Oops, sorry, I'm talking about things the other way around. Yeah, sorry. This is an active transformation when you're actually making a transformation to the object itself. A passive transformation, however, is a transformation of the coordinate system. So again, we can go back to the ship. We can describe it using curvilinear coordinates or rotated coordinates, but it just won't change the way the system is described. And you might think, how on earth is this useful? Well, this is kind of useful because if you can have multiple different descriptions of the same physical system, you can jump between them depending on the problem that you're trying to tackle, or the physically relevant quantity that you care about, because some coordinates definitely have an advantage over others when you're talking about particular things. So being able to jump between them is certainly it certainly can be an exam a very good strength. Sorry, so you shouldn't discount passive transformations, which are basically just coordinate transformations, as something of a mathematical fantasy, but it can be very, very useful when it comes to calculations. So yeah. So this is a very key point. So when a system displays invariance under passive transformations, that is to say, if so when I say system, I am talking about the equations of motion. Um, uh, I have this tendency to mix up these words, so I'll try to be explicit. So if the equation of motion is invariant, that is, it does not change under passive transformations, that's termed a redundancy. And if you have active transformations and it's still sort of invariant, you then term that as symmetry. Um, the two might seem similar right now, but when we are doing more explicit examples, it will become sort of more obvious. But Yeah, this is important. Again, like I said, you want to distinguish redundancies from symmetries, because there are a bunch of different other ideas in physics which we are not going to discuss, but symmetry is a very key element in them. If you've ever tried solving what is it using the mirror method in E&M, or if you're just trying to solve for like 3 or 4 chargers, symmetry can be very useful at that stage to sort of help you set the system up and sort of change frames and things like that. Or uh, I'm just going to throw this out here, but uh, symmetries are related. Okay, that's a very weird E. Symmetries are very much closely tied to conserved quantities. A person called Amy Noether sort of showed why it is so. Just mentioning it here in the passing so that you can look it up, or maybe we can have a discussion later on about it. But it's not very relevant to this paper, but it can be tied to it because we are talking about the same ground. So one way we're going to be sort of looking at things uh, is we want to sort of distinguish active and passive transformations because they have different consequences. So the way we're going to be doing that is by using something called bookkeepers. This is not a technical term, mind you. So the way we're sort of looking at this is we have these bookkeepers in the equation of motion. These are terms in the equation of motion. So when we make a passive transformation, the bookkeepers have to change to make sure the system, the equation of motion remains invariant as a whole. And for active transformations, this needn't necessarily be the case because they can, lead to different states. So yeah, again, I am not going to define this yet. Um, but yes, this is a important question as well, which we'll address. So yeah, so far we've understood the different types of symmetries and why they're relevant, and how we can sort of keep track of them, at least in a very intuitive sense. Again, I've not done a line of math or physics, so none of this means anything yet. So what we're going to do right now is again, this is an idea that's been floating around since the 90s, where people have tried to apply ideas from physics to the financial market, and we're pretty much going to do that. We're just going to apply the ideas of symmetries and redundancies to sort of exemplify it in the context of very simple markets. And let's start with uh, these guys. So yes, um, okay. So if if you have a vegetable market that has, let's say, some set prices for your different commodities, if you're going to scale the currency, the price of them will just adjust according to it. That is, obviously these are physically different ones, but the reason why we call them sort of symmetries is because, let's say, you can buy 3 tomatoes for €3 and 6 apples for, you know, €3. So you're selling your tomatoes at €1 and your apples at half of them. Now, let's say your currency drops by a factor of 10. You can still do this same whatever barter that you've set up. So physically, when you're talking about these quantities, it really doesn't change things, is the point. So this is usually termed as a global gauge symmetry. So the reason it's called global is because, again, you're changing the game, you're changing everything in the system at the same time. And it's a symmetry because you can see that it does not change what is physically relevant. And the word gauge, again, is just, again, honestly, I don't understand the origin of this word, but this is what we would term a gauge symmetry. That is, uh, this subsystem is invariant under a global change. And these transformations are termed gauge transformations, and this, since it is global, you call it a global gauge transformation. Again, a lot of words. But yes, now we can look at a slightly more nuanced one. And here what we're gonna do is we're basically going to set up a bunch of countries with specific currencies, and there's a sort of an exchange rate between them, right? And you want to see if scaling currencies at one particular point really makes a change or not. Okay, so that's kind of the idea as well. And we are introducing these bookkeepers again, and the reason we're introducing these bookkeepers is uh, we are assuming that if I am making a change here, that the exchange rates here, they adjust accordingly. So yeah, so we're going to start with so Germany. If you have one, if you have one quantity of DM in Germany, and then you go to United Kingdom, you have a 1:1 ratio, and then you have 1:2. So you go to France, you become richer. But then you go to Italy, you become more, you become a god basically. But when you come back, you know, it's it's basically all down to one. Again, this might seem a little confused, but there is no what is called a arbitrage opportunity. That is to say, you can't start with one DM and end up with two or three or more. You're not gaining anything. This is basically a zero sum game if you're going to do trade, if you're just going to trade currency this way. But of course, that is a case as well that we'll look at. There is no arbitrage opportunity. So the question here is, what would happen if one of these countries, so the example here is if the Italian government decides to drop a factor of 10 in its currency, and based on the assumption that the exchange rates change accordingly, which is an assumption, what happens? Do you have an arbitrage opportunity, or do you lose money, or do you gain money? And it's pretty simple. So you go one, and then you go to two, and then um yeah. So this is just the ratios. Sorry. So you're basically transforming L to this weird L, and this is basically given by dropping a factor of 10. Okay, so that's what we've done. And if you sort of work this out, you can see that this ratio would be sort of decreased. And the beauty about this is that if you start I mean like this ratio automatically gets adjusted. You still end up with a 1:2 uh, thing over here. And basically the loop remains the same. And this is what is called a local gauge symmetry, because what we've done is we've only changed the way currency works at one point, and that is basically not made a change to the system at all. So but yeah, again, at this point it is not clear if we are, again, this is the central contention of the paper. This is the central point that the paper is trying to deal with. Is gauge symmetry, is local gauge symmetry a redundancy or a symmetry? The reason you can't really tell is because, again, the currency that you're working with can just be thought of as a coordinate system. And you go into that whole mess of whether this is a redundancy or not. Again, it's also useful to sort of take a moment to pause and think if we should even care about this, now that I think of it. Because frankly, if a redundancy is useful, I think we should just leave it as it is. And we've already seen why redundancies can be useful. So yeah, there's a counter argument there as well from the opposite side of the aisle. So uh, what we've done in the next case, what the author does is we do go for a case with the arbitrage opportunity, and I'm going to stop here since I have sort of run atop of my time. Um, so what happens here is pretty darn similar, except that there's a quote unquote arbitrage opportunity given by the way the currencies are set up in each place in this system. So this is a pretty nice world to live in. You gain a lot by just simply trading currencies. But now the question is, let's say you make a local change, that is, you drop a zero in the currency eclipse. What is going to happen? So as you can see, I've just dropped a zero again in the Italians. So again, your money that is being earned is unchanged by this sort of local rescaling, and the final result is the same whether or not that you have arbitrage opportunities. So yeah, this is again uh, the point that the author is trying to drive here is that these exchange rates that are being automatically sort of updated are very, very crucial to this even being considered a symmetry. So these bookkeepers, these ideas, these imaginary entities that are automatically updating the exchange rates are crucial to our system. And that is what is presented in this point where uh, our bookkeepers are sort of important, but again, they are not dynamical entities yet. And the next example would be what would happen if they are dynamical entities, and uh, you know all the math that follows from that. So I'm going to jump from the paper here to the book that the same guy wrote. It's called Physics from Finance, and it's again the same thing, but I find that the calculations here are a little bit more detailed. So one second, I'm just going to show you what we're going to be doing next. This is a pretty cool thing to show uh, at the starting of this paper, because this is a very interesting technique that is being shadowed, basically lattice field theory technique. So what we're doing is, we're instead of talking about countries and stuff like that, we're just going to project it onto a lattice with a 2D lattice with a sort of a basis, and we're basically gonna talk about your exchange rates as functions of your position. So yeah, and the exchange rate, let's say, whoops, I can't write here. So yeah, so the exchange rate Ri of n is basically telling you, hey, I'm at n. What is the exchange rate between the country that is represented at n versus the country of n plus that ith basis vector? So basically, if it's one, if it's R1, this was E1 and this was E2, so it would be n plus E1. So this is, you just move one block to the right. And the point of doing this procedure is that it really sort of there's a more interesting point as to why people even do lattice calculations. Because sometimes they're just doable. You cannot solve them analytically, so you go by a discrete one, and then you take the limit, and then see if that thing converges. That's like the bigger idea of why people even do lattice calculations. But here again, we are following the same thing, but this wasn't exactly necessary, but I feel like the author does it so that the algebra is a lot more simple, and so on. But yeah, this is the route that we're going to be taking. Just projecting all these ideas onto the lattice and promoting our bookkeepers to dynamical entities, and then seeing what sort of things that we end up. And this is what really, really ties into the physics aspect of things as we go on. But yeah, that will be covered in the next session. You know, if for the interested people, there are some interesting pictures and some interesting words that are thrown around in this book. So you can sort of plot the exchange rate uh, in a way like this, and your transformations can be represented. Where was that pretty picture? Or am I missing it? Yeah. So there were just some pretty pictures that I thought I'd show. So yeah. So your shift, your transformations can be sort of described as like, so you basically you're thinking of the currencies as being a line at that particular point at that particular country, and your changes would be shifts in that single line. And this idea will be actually really really useful because uh, generally when we're talking about symmetries and things like that, the idea of groups, which is a mathematical concept, pops in. And when you're trying to describe the system, the set of transformation, the set of symmetries, basically ends up being something related to the real line. So yeah, there are a few more ideas here, but I guess they're more relevant in the later session, so I'll pause here.